Alright, hi guys. This video is going to be the first part of the backpropagation set of lectures. There's going to be two of them. This is just going to focus on a review of the prior concepts that we've discussed and some intuition as to um, what we're doing when we do backpropagation. So just to review, gradient descent is something that we talked about last time, and it's the algorithm that is used not just for neural networks, but many types of machine learning models, where we're trying to iteratively decrease the error of our model by moving our parameters of the model in some direction. And what that ends up amounting to is if you visualize the error as a sort of hill, right? Gradient descent is sort of like walking down the hill in the direction of steepest descent. Um, and the goal is to get to a sort of local minimum where, there's a flat point in the graph, right? Um, that's essentially what gradient descent is doing. So the reason why it's called gradient descent is that at every step here, we compute the gradient, which it actually tells us the direction of steepest ascent on our graph. So the gradient tells us what direction should we move all of our weights and biases in order to increase our error as quickly as possible. Now, obviously, that doesn't really make sense for us because if our error is a measure of how bad our neural network is, well, we want to make our neural network less bad, right? So since we have the information that the gradient points in the direction of steepest ascent, we just take the negative of that and we end up moving in the direction of steepest descent. And if we keep doing this over and over again, what ends up happening is we keep taking steps towards a local minimum. And then we end up reaching that local minimum, and then when we reach it, it's called convergence. Now, note that I'm saying local minimum here. Um, the reason why it's local is because just this iterative process does not guarantee that we end up at the global minimum. Uh, the place that we end up is actually just dependent upon where we start off, and also like the step size. How large are our steps when we're moving our parameters. So if we started off here, for example, on this point of the graph in this example, then we might have ended up here instead of finding this place, which looks lower, right? So it's not guaranteed to find the global minimum, so that's sort of an issue. But yeah, that's something that we have to deal with. So then, backpropagation in the context of neural networks is the process in which we compute the gradient for all the weights and biases of our neural network. The thing to note here is that a neural network is this huge composite function where the outputs of one layer are the inputs of the next layer, and the outputs of that layer are the inputs of the subsequent layer, and so on, right? So basically, the effect that some weight or bias has on the output of our network, there's many paths that it affects throughout our network, and I'll show you exactly what I mean by that on the next few slides. But given that um, the weights and biases affect the outputs in so many ways, like we have to take into account every single way that this happens. So in order to do this, we have to use something in calculus known as the chain rule. Um, and if we once we do that, um, you know, we're able to compute the gradient. So backpropagation is basically the process of iterative, it's a process of efficiently calculating the partial derivatives of the error with respect to the weights and biases of every single layer efficiently. And the reason why it's called backpropagation is we end up computing the partial derivatives of the error with respect to the weights and biases corresponding to the last layer first. So we start off computing the partial derivatives of all the parameters here, and then we move on here, and then we move on here. So, in a normal neural network, like when we're um, sort of getting our output, we do this, right? We move in this direction where the input goes here, and then we push the input through the neural network and get some output, right? So that's called forward propagation. But when we're computing the gradients, what ends up happening is we first have to compute this stuff, then we go on here, and then go on here. So since we're moving backwards, like as shown in this animation, um, that's the reason why it's called backpropagation. Okay. So before I get into backpropagation, though, I just want to talk about the sort of update rule that we use for gradient descent, right? This is basically the update rule, where the partial derivative of the error with respect to the partial derivative of some weight this is like the component of the gradient that what I'm talking about earlier, and by subtracting this, we're essentially moving in the direction opposite to what the gradient specifies, right? The gradient tells us the direction of steepest ascent, but by doing the subtraction here, we're moving in the direction of steepest descent. And so, this line basically says the new value of some weight equals the old value of that weight minus, I'll talk about what this is later. This is called the learning rate, but it's equal to minus the learning rate multiplied by the partial derivative with respect to that same weight. And so what this amounts to is basically we're moving in the direction, we're nudging this weight in the direction opposite to what the gradient told us to move in. And what this ends up doing is decreasing our error as quickly as possible. Okay, hopefully that all made sense. And the same thing we do for the biases too. It's almost the exact same update rule, but except we replace all the W's with B's, right? Other than that, it's the exact same. Where this is like the component of the gradient. This basically tells us, okay, what direction should we move this bias in order to get the direction of steepest ascent, and then whatever that value is, we move in the direction opposite to that, which is why we do this minus sign. All right. So this learning rate here is basically used to guarantee that we don't overshoot the minimum. And what I mean by that is, let's say we were performing gradient descent, right? And when we compute this minus, let's say we didn't have the learning rate, so try to don't look at the alpha value here, but let's just say Wi minus the partial derivatives of the e with respect to Wi. And when we compute that, what we end up doing is, sorry, let's say that, since the gradient would point in this direction, and we're moving in the direction of steepest descent now, the gradient would tell us, okay, move your x position on this graph to here, right? Move it in this direction. But if the gradient is too large and we actually end up moving it all the way over here, well, we kind of got worse there, didn't we? Because ideally, we'd want to keep moving here and here and here and stop once we get to this minimum. But since the magnitude of the gradient was so large at this position, the gradient basically told us, or the direction, the negative gradient told us to move over here. It told us to move the x position all the way here. And that basically made our error even higher than it was before. We don't want to go up this graph. We want to go down and then stop here. So by using this alpha term, which is usually a value between 0 and 1, what we end up doing is limiting like the magnitude of our gradient, right? Like decreasing the magnitude of the steps that we take, so that instead of having this where we like we completely overshoot this minimum here, which is the point that we're trying to reach, we successfully decrease, like we take smaller and smaller step sizes when we're getting to the minimum here. I mean, not smaller and smaller, we just take small step sizes until we reach this point. Okay, hopefully that made sense. And before I go on, I just want to talk about a key difference between several types of gradient descents that you might see. So there's three types that I'm going to talk about. One is stochastic gradient descent, where we perform this sort of backpropagation process and compute the gradient for every single training example in our training data set, right? This is in contrary to batch gradient descent, where we actually, we store all of these values. We calculate the gradient every single training example, but we store all of these. We don't like make any changes, but we store all of them. And at the end, once we've seen every single training example in our training data set, we average the changes that we would have made at each individual training example, and we average all of those and then make a step in that direction. And then mini batch gradient descent is sort of a hybrid of these two, where we don't step after every single example, but we also don't wait until we see the whole training data set. We maybe see like 8 or 16 of them, and then we take a step. So if you visualize like let's say this is like a plot of our error function here. The purple line here corresponds to stochastic gradient descent. And the reason why it's so like violently like sort of it's really weird is because you're taking steps after every single training example, so it's going to be jagged, like it's not going to be a smooth learning process. Whereas a mini batch gradient descent, where you take a couple of them and then average out the results, that's a little bit smoother, because when you take the average of them, it sort of evens out the changes that you make. And then batch gradient descent is just the smoothest, because you're taking the whole training data set into account, so all the changes are going to be averaged out. Okay, and now going back to the composite function idea, let's say we define this error function of ours as this, where, just to be clear, N8 corresponds to the output of node 8 here, or neuron 8, and then N9 corresponds to the value of neuron 9. And Y1 and Y2 are the sort of, those are the correct values given some input. So let's say we fed in some input here. Y1 and Y2 would be the correct outputs given that sort of input. And what I mean by correct is, it depends on the task, but those are the sort of items that we got in our training set. And so if you look at this error function, what it's essentially doing is calculating the difference between the values of node 8 and y1. Y1 would be like the correct output here, and then y2 would be the correct output here, right? So what we're basically doing is calculating how different are node 8 from y1 and node 9 from y2, and we have this factor 1/2 here because later on it makes things easier when we're doing like partial derivatives, but don't worry about that for now. But let's say we want to calculate the partial derivative of the error with respect to weight 4/8, which is the weight that connects neuron 4 to neuron 8, right? Well, in order to do this, we have to consider two things. We first have to consider, okay, how does the output of neuron 8 affect the error? And then we also have to consider the effect that this weight 4/8 has on neuron 8. So we have to basically the combined effect that the partial derivative of the error, okay, the combined effect that weight 4/8 has on the error is going to be the effect that weight 4/8 has on neuron 8 multiplied by the effect that neuron 8 has on our error function, right? That's sort of the path that weight 4/8 affects the error. And if we move on to a weight earlier in our neural network, right, it gets even more complicated, because we have to consider all the paths that this could possibly affect the final error, right? So if we're calculating the partial derivative of the error with respect to weight 1/4, then we have to consider, okay, how does neuron 8 affect the error? How does weight 4/8 affect neuron 8? And then, sorry, not weight 4/8. How does neuron 4 affect the value of neuron 8? And then how does weight 1/4 affect the output of neuron 4? And we also have to consider, okay, how does neuron 9 affect the error? And then how does neuron 4 affect the output of neuron 9? And then how does neuron 1 affect the output of neuron 4? Or not neuron 1, weight 1/4 affect the output of neuron 4. And then we have to like do this whole thing, right? So as you get earlier and earlier in the network, the number of paths that some parameter affects the error through increases like very rapidly, right? So it becomes like quite complicated. But there's actually a very y the trick of backpropagation is that a lot of the computations here are actually repeated, so you don't have to do a lot of work. Before we get into like the exact formula for backpropagation, um, just want to talk about two things. One is the Hadamard product, which is just element-wise multiplication, right? So if you have these two vectors, 1, 2, and 3, 4, and you're calculating the Hadamard product of those two things, this would just equal 1 times 3, and then 2 times 4, which equals 3 and 8, right? The constraints for this are that the two vectors or matrices have to have the exact same dimensions, but other than that, it's just simple element-wise multiplication. Okay. Another thing that I just wanted to review on is the sigmoid function. And the sigmoid function is basically a nonlinearity function that allows our neural networks to learn more complicated functions. If you don't exactly remember this, I highly encourage you to review the last neural network video. But basically, all you need to know is that this function allows us to learn more complicated tasks. And something to note is that a reason why the sigmoid function is used is that its derivative is actually just itself, like the sigmoid function multiplied by 1 minus the sigmoid function. So when you're doing backpropagation and you have to calculate the derivative of this, it becomes very easy if you've already stored the value of the when you were doing forward propagation. Okay. And lastly, I just want to talk about a vectorized neural network, which basically is you know if you're also not familiar with this, I highly encourage you to watch the last video. But basically, we store all the weights and biases as matrices and vectors because one, it helps us organize things as a programmer, and two, if we write our neural network in terms of matrix multiplications, it allows us to drastically speed up computation, especially if we're using a hardware accelerator like a GPU. Okay, so uh, weight 1 here corresponds to all the weights in this layer. Weight 2 corresponds to all the weights in this layer. Um, X0 corresponds to the inputs, right? X1 corresponds to all the nodes in this layer, and X2 corresponds to node the neurons in this layer. And then bias B1 corresponds to all the biases for this. Note that we don't have any bias terms here because this is actually like these circles represent the inputs, right? These are not like neurons. These are just inputs. Okay, so B1 corresponds to everything here, and B2 corresponds to the biases in this area. And then Y1 and Y2 correspond to the outputs. And then just if you're writing the outputs of this neural network in terms of these matrices and vectors, then X1, which is the outputs of this layer of neurons, that's basically equal to the sigmoid function of weight 1 multiplied by X0 plus B1. And then once you take that output, which we store in X1, you just do a similar process to calculate the X2. And that's our final output of the neural network. Okay. And so before going on, I just wanted to talk about, given the vectorized form of the neural network, what are we trying to create using backpropagation? Like what form should our partial derivatives be structured in to take advantage of the vectorized form of our neural network, right? So just using the same structure that we organized our weights and biases in on the previous page, like for example, this is the same exact weight matrix that you would have seen on the previous slide. We basically just want to create a matrix of partial derivatives where in each location there is the partial derivatives corresponding to the specific weight that was located in the same location as um, in the original weight matrix, right? So this is the partial derivative of the error with respect to weight 1, 4. And if you look at the same spot in the corresponding weight matrix, we see weight 1, 4, right? So these are exactly like matched. And if we have these sort of weight matrices in this shape, and the corresponding partial derivative matrices of the biases as well, we can basically just repurpose. It's the same exact learning rule, where here, instead of having the partial derivative for some specific weight, we just have the whole matrix. Like this would be some whole matrix, and this would be the corresponding weight matrix. So this is the weight matrix, and this is like this one or this one, right? And same thing for the biases. Note that the dimensions have to be exactly the same, but that's a given, because if we have a partial derivative at every single location for every single weight, then it should, by definition, be the same dimensions, right? So using this, the formulas on the next page or the next slide will tell us how to come up or create these sort of partial derivative matrices. As to our final formulas for backpropagation in a vectorized neural network. So in order to implement backpropagation, you first have to compute these things called delta matrices. And these delta matrices basically represent a lot of the shared computation that occurs when you're running a neural network, right? So when you're running backpropagation. So to compute the delta matrix for the last layer, and note that when we're computing these delta matrices, we start from the end of the neural network and work backwards, and that's why it's called backpropagation. So when we're computing the delta matrix for the last layer, we first have to, in this case, L would be 2, right? Because 2 is the final layer here, and so we do x2 minus y, which is sort of like the component of the error that we want in our terms, and then the Hadamard product of that with basically the outputs of the neural network for this layer, except instead of putting this weighted sum plus the bias through a sigmoid function, we actually put it through the derivative of the sigmoid function, right? And it turns out that this vector and this vector will end up being the exact same dimensions, so we can compute this element-wise multiplication, right? So even though this might look complicated, note that all of these things are elements that we already have if we've successfully conducted forward propagation, right? XL is just the outputs of our network. Y is like the correct example, if we have numerous sets of, correct pairs like train and we have a lot of X's and Y's basically, then this should be already given to us. And then the weights, those we already have, right? Because if we implemented forward propagation, we must have those. The activations we also have if we stored them from forward propagation, and the biases we also needed to have for forward propagation. So everything here is something that we already have, and it's just putting these things together in this way that lets us arrive at this formula, right? And then to compute the delta matrices for layers earlier in the network, we use this formula where I is just whatever layer index we care about. So for example, if we're the only other layer in this except for layer 2 would be layer 1. So the delta matrix for layer 1 would be the weight matrix transposed of layer 2 times, and this is a matrix multiplication, times the delta matrix of layer 2. And note, this is the delta matrix of layer 2, which is exactly what we computed over here when we were computing delta L. So that kind of shows where we use this where we reuse this computation, right? We didn't have to do all of this again here if we had saved this successfully. So that's why it's important to save your delta matrices. And then you take all of this and then perform the Hadamard product with this term. And this is very analogous to this, except instead of L's, we replace them with I's, where I represents the current layer, right? So this term basically represents the outputs of all of these neurons, except we didn't put it through the sigmoid function. We actually put it through the derivative of the sigmoid function. Okay, cool. And so now, if we've computed these delta matrices for every layer, then in order to compute the partial derivative matrices that we talked about earlier, for some layer I, it's simply just the delta matrix for that layer times the transpose of the outputs of the previous layer. And note that this is going to be the exact same dimensions as our corresponding weight matrix. And similarly, actually even more simply, for biases, to create the bias, the partial derivative of the bias vectors or matrices, those are just literally just the delta matrices, right? So there's nothing else that we need to do. So this sort of illustrates the beauty of the fact that we don't have to do much work. Like writing backpropagation out like this actually saves us a lot of time, especially if we have like GPU accelerators. I mean, hardware accelerators like GPUs. And so yeah, that's it. Hopefully, I know this can be complicated, but don't be scared off. As I said, all of these things are just items of our neural network that we already have if we've successfully run forward propagation. So implementing backpropagation is just a matter of putting everything together. All right, cool. Thank you for watching.